Okay, so this right here is going to be an introduction to how acids and bases work. Now, after this video, you should not have full mastery on how this whole thing works. You should be, say, like halfway there. And the annoying part about this is not really annoying, is if you follow the mouse, we form something called hydronium, and the way it forms is a little bit complicated. So this is something where it's not hard. I can explain it really well over not just today. You're going to see another video tomorrow where I kind of explain it my own way. You will get the idea, you will understand it, but don't obsess over some exceptions for the rule. Is why does hydrogen then bond with oxygen? It's very complicated. It's something you probably won't even touch until AP Chem, and I'm not even sure if they do acids and bases in honors chem. They may. I'm not sure about that. So we've done it in Challenge Science every year because it makes sense. So just go with the flow. It's really not hard to follow. So this is just going to be an overview. And what I'm going to show you is we're going to add a strong acid to a beaker, a weak acid, a strong base, and a weak base. And you're going to see what happens. And I'm going to kind of translate all this crap down here. So, and then we're going to do something else. But this is part one. So you need to take notes. And hey, you could sit here and snooze, whatever. You're wasting your time. Just don't even take notes. I don't care. This is for kids, and this is for, I would say, almost everybody. I know there's some kids that, you could tell that aren't doing what they need to do. Dude, you is wasting your time. That's fine. This is for kids who have been really trying, and just keep learning, accumulate the knowledge. So watch closely. All right. So right here I've got water. And water has a pH of 7. It's neutral. It's neither acidic or basic. It's right in the middle. So is there a little bit of hydronium? Yeah, H3O. Is there a little bit of OH negative, which is basic? Yeah. But what I want you to understand is this. I want you to just follow what happens and just bear with me. And don't freak out after today. It'll be even more clear after tomorrow. I think by Wednesday you'll be good to go. All right, here we go. So I'm going to stick this pH meter in here, and it's going to be 7. And now I'm going to click on strong acid. And I will tell you this, a strong acid. Now this is where we know about dissolving. Remember we talked about ionic compounds dissociate. Strong acids, and you see where it says HA? H means hydrogen, A means like Cl, like the anion. So it's H with whatever anion. Does that make sense? That's what HA means, all right? So strong acids dissociate 100% completely. Weak acids dissociate up to about 90 to 95%, not completely. So some don't dissociate at all. So let's see what happens when a strong acid goes into this beaker. I'm going to take the pH meter out and watch what happens. And I'm going to show you real quick. The solvent, so right here is the water. So predict, what do you think is going to happen? Let's see. So what you have here is we dropped in acid, and what happened was, pretend it's HCl. So here's the H, watch the mouse, A anion, Cl, notice the radius, okay? Over here, you got water. What do we have? It's just showing dissociation. We've got the anion, the chloride, salt, the blues right here, right? And H3O, it's whatever water accepted that extra hydrogen. So see this little red dot right here? One of these three was attached to this. They split. Do you notice that we have 100% dissociation? There is no acid still stuck together, undissociated. So a strong acid dissociates completely, 100% in water. And now predict, what kind of pH would you expect? It would be a very low pH, because the higher the concentration of dissociated hydrogen, which leads to hydronium, right? The lower the pH. So drop this in here, we have about a pH of 2, okay? So again, 100% dissociation. Okay, I'm now going to take this out, and we'll go back to water. So now let's take a look at a weak acid. And weak acid, same structure, H, here, look at the mouse, hydrogen with the anion over here, the negative anion. Okay. So we're going to see what a weak acid looks like, and then we'll compare the two again. Oh, okay. No, I'm not surprised. I'm acting surprised because I've done this for years. So right now you've got the acid, which is not dissociated down here on this formula, with water. And this means they can be reversed because this dissociation, they'll go back to each other once if you evaporate them away. Okay. So you note, what do you notice here? A lot of undissociated, right, acid. Less dissociated, there's less, we put the same amount of acid in as we do with strong. And you notice that, yeah, there's some dissociation. You see some hydronium, but there's still a lot that has not dissociated. So if there's less dissociated hydrogen and there's not as many anions, what do you project the pH to be? Is it still acidic? Yes. But it's going to be higher than 2 because it's a weak acid. Weak acids do not dissociate 100% in water. Now again, acids are beyond polar. They will dissolve in water, but will they dissociate? It depends. Now let's take a look. Instead of a 2, you've got about a 4.5. So you see this visual. I'm going to click right on strong acid. Wait till you see the difference. Notice here you've got some blue anions dissociated from hydrogen ions, right? And there's a lot of undissociated acid. What happened when we had a strong acid? Do you see any of these in here? No, because a strong acid dissociates 100%. Therefore, allowing a lot of free hydrogen to go towards the water, therefore allowing a very low pH, because pH depends upon the concentration of hydronium ion dissociated hydrogen, okay? So strong acid, 100% dissociation. Weak acid, meh, some dissociation, okay? All right, so let's go to bases. Let's go back to water. So now we're going to take a strong base. Now, they're ionic compounds, and a lot of these will dissociate no problem. So when we see, what does M stand for? Think about it for a minute. Think you have the answer? What's the charge of the first ion? Positive. What is that called? A cation, where cations on the periodic table. On the left side, what is the left side called? Metals with the hydroxide polyatomic ion. So let's take a look at let's start with a strong base. So right now, let's see how many hydroxides we get. So notice you have your potassium hydroxide, KOH, or sodium hydroxide. Notice, complete dissociation, we have the metal ion that's stable. See the orange, yellow guys right here? And we have the hydroxide ions fully dissociated. So the higher the concentration of hydroxide, the less hydrogen, there's hardly any in there, therefore the higher the pH. Okay, complete dissociation. How do you think a weak base will look? Base in water, a weak base. What do you notice? Some of them dissociate, some do not. Okay, so again, not full dissociation, and therefore there could be an extra little bit of hydrogen in there. pH is not as high. So pH for a strong acid, 100% dissociation, lower pH, lots of dissociated hydrogen. Weak acid, some dissociation, not as much H3O, which came from the dissociated hydrogen, higher pH. Strong base, 100% dissociation, so there's really no hydrogen in there by itself, therefore stupidly high pH. Weak base, basic but not that high, okay? All right, so now let's take a look at this. Let's go back. Let's do a conductivity test. And this goes back to ionic and covalent compounds. So if I stick this in here, because of some dissociated substance in here, you have a little bit of conductivity, because you should remember that ionic compounds, when do ionic compounds conduct electricity? You need to know this. If you can answer this to yourself, then you're great. If not, you got a problem. You better go back and restudy. So when do ionic compounds conduct? Can they? The answer is not at all. Well, you said no. I said ionic compounds do not conduct electricity. Ionic compounds, when they what? Dissociate, conduct electricity. So then your question is this. If I were to make this a strong acid, would this change at all? And if it did, how would it look? And if it doesn't, why? If you can answer that correctly, then you know what you're doing. I'll give you a second. If I put a strong acid in here, what will that light bulb look like? The answer is, given the fact that we have complete dissociation, very bright. Why? There's a lot of ions floating in solution, which is the flow of electricity. See how the stuff comes back? What about a weak acid? Ask yourself, one, is there dissociation? Yeah. Is it an ionic compound? Yeah, but it's not as much dissociation. So it won't conduct at all? No, it still will, but what? Not as much, because there's not as much dissociated ions in there. Whereas here, you got a crap load of dissociated ions flowing in that joint right there. You see how that works? Okay. Go back to water, where there's minimal ions in there, little conductivity. So let's put a strong base. What do you know about a strong base? Complete dissociation. Predict what's going to happen to the conductivity tester. Is a strong base an ionic compound? Darn right it is. Do ionic compounds conduct heat and electricity? Only when what? Dissociated. Bam. Weak base, less dissociation? Less. Okay? All right. Here's just a pH strip. You could see, dip it in, match it with the color. It gives you about a 10, 9.5, 10, 10 more so. Strong base, dip it in. Litmus paper, pH paper. This is about a 12, 12.5. This has about a pH of about 2. Weak acid, pH of about, dip that more in there, pH of about 4 to 5. Okay? All right, so now let's do something else. Let's go to, hold on, how do I do this? Okay. So now let's look at molarity, let's look at concentration. And let's increase the strength of let's start with a strong acid. Okay. Let's start with a lightly concentrated. Let's say we didn't put much in there. What do you think the pH is going to be? Low. Why? Because even though you put a little bit in there, it completely dissociates. 100% low pH. What happened if I increase the molarity? More dissociation. pH drops considerably. See how that works? 100% dissociation. Okay? All right, now, let's use a weak acid. Weak acid, weak acid. Drop it in. What do you see? I keep getting undissociated material. Now, what do you notice? It's still dropping in pH, but what? Not as drastic. Why? Because there's just not much dissociation going on. So let's go back here. So our initial pH is 6.5. If we increase it, it doesn't dissociate much. Our pH only dropped to about 5. Okay, so we added the same amount of, so we went from 0.001 molar to 1 molar, weak acid, weakest you could have, and you only drop by about, what was it, 1.5 in pH. Look what happens, not much dissociation. And again, put the conductivity tester in there. You've got some light because you have ions in there, but not too much. Let's go back to that strong acid again. You're starting at 3. As you add more and more, look at that, 100% dissociation. Look at the major shift in pH, not by 1.5, by 3. Because why? 100% dissociation. And what do you predict the conductivity test will look like? Whoa, that's bright. See how that works? So as you increase the concentration of an acid, 100% dissociation, more of a pH shift, until it becomes what? Saturated. Because once the solution becomes saturated, you're not going to be able to dissociate anymore. And that will get into titrations. We don't go that far, okay? But yeah, this stuff does build, okay? But you don't have to worry about that. Don't worry about saturated, unsaturated. We're going to stick with unsaturated for now. But yeah, eventually it becomes saturated, it can't dissociate anymore. Okay, so let's go to the base. Start with the weak base. So right now, our pH is 7.5. So we have a weak base, so you're not going to see much dissociation. So we're going to go from 7.5, increase the concentration, same thing, 0.001 to 1. We're adding base, but it's not dissociating. We're adding base, but it's not dissociating. We're adding base, but it's not dissociating much. So we went from 7.5 to 9. Hardly any dissociation. So the pH went up a little bit. Have some light. What happens if we put a strong base in there? The base, start here. Strong. Yeah, strong base. Shoot, we're already starting at 11. Boom, we are up by 3. 100% dissociation. Whew, there you go. So at the end of this video, all I need you to understand is this. Strong acids and strong bases dissociate 100% completely and have a greater shift in pH. Weak acids and weak bases can still dissociate, but not as much. The pH shift isn't as much, okay? And you know that they can conduct electricity when they dissociate. So tomorrow what we're going to do is this. We're going to talk more about the dissociation and kind of where things go, okay? And it should make a lot of sense. And then we're going to talk about, well, how do I neutralize acids and bases? So we'll get into that on Tuesday and Wednesday. And then by Thursday, you guys should be able to move on to predicting products. So again, this will be 4 to 5 days on acids and bases. And I'm not going slow because we're behind. I'm going slow because we're ahead. And this is a luxury because I've never had this much time to go over things. Again, it's not that you're not capable. We're learning more than before because we're taking our time. You don't have the PSSAs. You would have just finished your PSAs last week. Let's see, tomorrow would have been Ion Insanity. You would have finished nomenclature. You would have had an exam on nomenclature like, let's see, Tuesday, Wednesday, or Thursday, something like that. That's how far ahead we are. So that's why we are in a great spot. We have learned more and we are taking our time. So pay attention, and this is a great opportunity for you people. And I'm going to keep throwing the review at you so it sticks up here. Okay, that's it. That will be the video. Good job.